Hello everybody and welcome back to our AI course for biotechnology. In the last session we have learned about machine learning, about the different machine learning types like supervised learning and unsupervised learning, and we have looked at some examples. In this session we will look at the first machine learning model and we will have a deeper insight into the model, how it works. The model is called Nearest Neighbor, and before we start with this I would like to give you an overview about the machine learning workflow and what is necessary to apply machine learning on real data. So the first step in a normal machine learning project would be the data collection step. Before we can do anything, we have to collect data and we have to label the data. That's a very long and detailed process that has to be very well planned. So don't underestimate this data collection step if you start a new project and there is only a very limited number of data available. The next step, which usually takes a lot of time, is data pre-processing and data cleaning. So these two first steps make usually 80 to 90% of the work when you do machine learning projects. So first you have to collect the data, then you have to inspect the data, you have to clean it, you have to pre-process it, and so on. So this is a lot of work and should not be underestimated. The third step in a machine learning workflow is then the model selection and the model training. So here we do more or less all the magic. So here we train machine learning models, we select the best performing model, and we evaluate the models. After this step, usually there is a fourth step. In the fourth step, we usually try to gain insights from the machine learning model. We like to do inference. We like to make predictions about the future and learn something from the data. And in the fifth step, we usually deploy the model that it can be used in real-world applications. So in this lecture, we will mainly concentrate on the middle part here at step 2, step 3, and step 4. The first step, the data collection, we usually let do by others, and we also won't talk in this lecture about the deployment of models. So before we can do any machine learning or before we can train any model, we have to learn about some basic terminology and notations. This is something very important because this is different from domain to domain. And also, if you read machine learning publications or papers, different authors use different notations. So in this course, I like to define in the beginning how we name things and how we display some of these things. So let's first look at the data. So data representation is a very important step. So usually in machine learning, data is represented as the follows. So we have usually some samples. Samples are sometimes also called observations or instances. And so we have 1 to n samples. So the total number of samples is usually n. And they are usually illustrated as rows. So each row is one sample. Then for each sample, we have up to m features. Features are sometimes also called attributes, measurements, or dimensions. So what could be, for example, a feature? A feature could be, for example, a specific measurement, like the height of a plant, the biomass of a plant, the color of the flower, the number of leaves, the number of seeds, the number of roots, and so on. So features are nothing else than measurements. That's why they're also sometimes called measurements or attributes. So we have here now a data matrix. The data matrix has n rows and m columns. And xi1 to m are the features, and each sample has a number of features. And then in addition, we have the label. The label could be, for example, a class label or a continuous label. So for all our samples from 1 to n, we know which sample has which label. For example, let's say we're talking about disease. Then the label could be either this sample or this patient has the disease or it has not the disease, and so on. So in this vector, we can write down the class label, or if it's a continuous label, for example, the price of a house. Let's say each sample is a house number 1 up to house number n. Then we can write down here the price of the house and here the different features of the house. For example, one feature could be the area of the house, the number of rooms, the number of windows, and so on. Mathematically written, it looks the following. So we have uppercase bold letters. They are used to refer to matrices. So here, uppercase X is element of the real numbers, which has the following dimensions: n times m. And n is the number of samples, and m is the number of features. That we usually use to denote the data matrix. And y are usually our labels, and for vectors we use lowercase bold letters, and with this we refer to vectors. For example, y is element of the real numbers and has dimensions number of samples times 1. If we talk about classification problems, for example about binary classification problems where we only have 2 classes, like someone has a disease or not, then it's we have only 2 states like 0 and 1, and then we denote here not a real number, or we don't write a real number, we write just the class label 0 or 1. So now let's look a little bit deeper into the matrix X. So I said we have m features and n samples. We use the index here the 1, the 2, or the m to denote the feature number, and the superscript here, superscript 1, we use to denote the sample. So for example, if we use lowercase italic letters, we refer to single elements in our matrix or in our vector. An example, if we write here x index 1 superscript 2, then this element refers to the second row, because we have here the 2, so it's the second row and the feature at position 1. So here, that's this element then. So row 2, column 1, or sample 2, feature 1. And if we write y superscript 2, then we refer to the label of the second sample. Please also note that the superscript here should not be switched with the exponentiation. So it's not an exponentiation, it's just a superscript that indicates the sample number. We also then can write vectors. So if we write lowercase bold letter x index 2, then we refer to a column vector of feature 2. So we said the index refers to the feature, so that's then the vector of feature 2. So all the values from this column here. So feature 2 for across all the samples. And if we write lowercase bold letter superscript 2, then we refer to the second sample. So that's then this sample here with all the features. So here we have the row vector with this, and that's the column vector down here. And then with this we can now define what a data set is. So a data set is a set of the following tuples. So we have here a tuple, bold lowercase letter x, superscript I, and then here the y superscript I, and this is a tuple for all my n samples. So this means that x superscript I is the row vector of m features for sample I, so that's for all the samples, and y superscript I donates the label for the sample I. That's our data set for all our samples n. And with this, we now can start to define our first machine learning model, namely the nearest neighbor model. And what will we learn here? So we will learn about what is nearest neighbor and what is k-nearest neighbor. We will learn about how we can train and predict with this model, and we will learn how we can do classification and regression using the nearest neighbor model. So let's motivate this example. So let's look at the following. We have here data points for two different classes. Let's say the orange points are dogs and the green points are cats. So now the question would be, if we have here this blue dots, what is the class of this unknown data plots here? Does it belong to the class of dogs or to the class of cats, or to which class does it belong? That's what we like to do. So what or how could we do this? So what we could do is we could very easily, if we look at this plot, make predictions based on the most similar points in the neighborhood. And that's the idea of k-nearest neighbor. So we make predictions like here or like here based on the most similar points in the neighborhood. But what's with this example here? For example, here we have green ones in the neighborhood. Here we have orange ones in the neighborhood. So how do we do predictions here? And there we look at the k-nearest neighbors. So we not only look at, for example, the closest neighbor to one neighbor, we look at several neighbors, and then we do predictions. For example, in this case, we say, okay, we look at the three closest neighbors, and here in the three closest neighbors, we would then say, okay, there are two orange ones and only one green one, so we predict this unknown data point to be a dog. So that's the basic idea behind the k-nearest neighbor method. And if, as you might guess, k-nearest neighbor is one of the simplest supervised machine learning models. However, even if it's simple, it does not mean that it's not used anymore. It's still very much used in different areas. For example, in recommender systems, if you like to recommend to a user a movie that he might like or a product that he might like, or it's also used in pattern classification or in imaging. And k-nearest neighbor is also a very good benchmark. So what do I mean with a benchmark? Benchmarks are comparison partners. So when you develop a new machine learning model, or if you use more complex models, you always should compare to very basic, very easy models to get an intuition how, if it's worth to take the more complex model, or if you could also achieve these results with quite easy models. And k-nearest neighbor is a so-called lazy learning algorithm, or also called an instance-based method. Why is it lazy? It's lazy because there is no real training actually happening. The training of the algorithm is nothing else than just storing all the labeled training examples. So we don't train anything, we just store all of them. So our data set D is already our trained model, more or less. We don't have to do any training. So how do we do then prediction if the training is so easy? So the prediction is done as follows. What we do here is we find the k training instances that are the closest to my query point x superscript q in my dataset D. So first, we find the k training instances that are from the distance very close to my point x q in our dataset D, and then we predict the label of this unknown data point x superscript q based on its similarity compared to the stored instances. And here, this with the similarity, that's where the magic happens in our k-nearest neighbor classifier. And I will come back to this later, how we can determine the similarity. So how does the classification work now? If we look at classification, the prediction works as follows. We do usually a majority vote. So we predict the class of the most frequent label among the k neighbors. So we first try to find the k closest neighbors to our query point x, and then let's say we have found 10, the 10 closest neighbors if k is equal to 10, and then we try to predict the label based on all our neighbors, and herefore we just take the majority. So let's look at this example. Here we have 4 blue squares, 3 green circles, and 3 orange triangles, and then we just look at the frequency of these items or of these classes. These are all our 3 classes. Then we see the squares are more frequent than all the other classes, so the data point xq, our query point, will be assigned the label of the square. That's quite easy. That's classification in this case. And regression is also quite easy. We just take this 10 points, this k points, this k closest neighbors, and we compute the average, and then we predict or we use the average to predict the query point to be this average. So, as I said, we like to do prediction. And when we do these predictions, as I said, we try to find the dk, the set dk, that's the closest points in my data set D to my query point xq. So this is our sub data set dq. And then if we like to do prediction, then it looks as follows. So we said we do the majority vote. So how does the majority vote look like when we write it down with math? Here we have our y superscript I. So this is element of 1 to t. So these are my t different classes. So if it's a binary classification problem, we have 0, 1, or it could be also 3 classes or 4 classes. So this is out of this set of my classes, the different classes. And then when we like to predict the label for our data point xq, the prediction we usually call y hat. So the hat above here should indicate that the y is predicted. It's not a y that we are given from the training data set, it's a y that we like to predict. So y hat is our prediction for the query point xq, and we compute the prediction as follows. Y hat is equal to the argmax of all our classes. So we like to find the class with the maximum number of the following. So what we do here is we compute the sum for all our training instances in our dataset dq at dk, and dk is our dataset of the most similar instances to q. So this is our reduced dataset here of our k closest distances. And then we have here the so-called Kronecker delta function, and the Kronecker delta function is equals to 1 if a is equals to b or 0 otherwise. This means, let's say I take here the first class, then I compute the Kronecker delta of all the points in my sub-data set dk, and I check how often do I find class 1 among all the labels, and I sum this up for all the classes. So I get then for all my t classes a number. For example, for my first class I might get, okay, if k is equals to 10, 5 of my data points are belong to class 1, and 4 data points belong to class 2, and 1 data point belongs to class 3. And then we take the argmax, which tells us then which of the classes has the highest count. And then we could compute with this formula the majority vote. And for regression, it's even simpler. For regression, we compute the average across all the closest data points which we have found for xq, and that's our prediction y hat. So we have now seen what we have to do predictions. We first have to find the closest data points to our query data point, and then we either do a majority vote or we compute the average across all the k closest points. So let's look at an example. We have here 42 data points and 3 classes. So y is element of 3 classes. This green circle is one class, the blue square is one class, and the orange rectangle is the orange triangle is one class, and we have 42 data points, 42 samples. So our data matrix X is then equal of R, 42 samples, X2, 2 features. So we have 2 features, we have the X1 and the X2. So for this 42 samples, we measure 2 features, and this are illustrated in this scatter plot. So for example, this sample here is my 12th sample in the data set, where when we write here bold X superscript 12, then we get here the following row vector. So that's all the features for this sample 12, and this is the following data entry. So all the features for sample 12, and here we have the label. The label is the green circle. And what we like to do now is we like to predict here for this star, we like to predict the label. That's an unknown data point, and the prediction task is, can we infer what is the class of this data point? Now let's take an example. Let's say k is equals to 5. So we try to first find dk, which are the 5 closest neighbor to my point. So for example, in this case, these are the 5 closest neighbor. And then I do a majority vote. I look at the distribution, how often do I find the square, how often the circle, and how often the triangle. And in this case, the square we find 3 times. So this is the majority class. So we predict this data point to be the square. However, if we now look, for example, at k is equal to 14, then we compute the 14 closest point, or we try to find the 14 closest point to my star, which in this case are the following points. And then our prediction would change, because then it says the majority of these 14 points is not, in this case, the square anymore, it's the triangle. So in this case, when we select k is equal to 14, our prediction is the triangle. So now the big question is, how should we select k? What's a good k? What's a good choice for k? And that's an interesting and a very an interesting question. So, for example, if we look at the extremes of k, if we set k is equal to 1, then we only look at the closest neighbor. And this very often leads to noisy predictions, because then we just infer the label by looking at our neighbor, and we don't and we ignore all other data points. If we go to the other extreme and we say k is equal to n, so to the number of samples, we look at all the neighbors that are in my dataset. What we then would do is, then we just would predict the majority class in classification problems, or the mean value of all the instances for regression problems. So if k is equals to n, we only look at how many patients got sick and how many patients are healthy, and then we predict, okay, the new data point has to be healthy because more than half of the patients are healthy. So that's then also not good. So how should we then set K? And this we will learn in our next lecture when we talk about model selection and evaluation. So a lot of these models which we will learn about in this course will have different values which we don't know, these parameters here. And in this case we have the parameter K, and this we have to set. And one of the methods is the so-called cross-validation, and this we will look at in the next lecture. And for binary classification problems, there is one hint. There we usually should choose odd K values, and that's to avoid ties. So for example, if we have a binary classification problem and K would be equal to 10, and we have a tie of our closest points, so 5 belong to the one class and 5 to the other class, then we have a tie, and then it's difficult to decide what is the majority class. And therefore we usually take odd values because then we always get a decision. So let's look at an example. Here we have two classes again. We have this blue class and the orange class here, which is in the middle of the blue class. If we now take, for example, K is equal to 1, then we see here the decision boundary. So we just look at the closest neighbor and we do our predictions. If we use K of equals to 3, we see that this decision boundary gets a little bit larger. So we also look at more neighbors in the neighborhood. And this is getting more and more extreme. So if we select K is equals to 10, the decision boundary gets smoother. If we select K is equal to 50, so we look at the 50th closest point, then the decision boundary of our classifier gets even larger. And if we select K is equal to 150, then we just do a majority vote. So we would then assign all the samples to either one or the other class. And this K is a so-called hyperparameter that has to be chosen by us, and how we choose this we will learn in the next lectures. So let's go back to the K nearest neighbor method. We said we have to find the K training instances that are the closest to my query point X superscript Q and predict the label based on its similarity. Now is the question, how do we find the K instances that are the closest to my query point X, Q in my dataset D? And there we have to look at so-called distance or similarity measures. So the following we will learn what are distance measures, what is a metric, and what are basic distance measures that we will use, for example, for the K nearest neighbor method. So first we have to do a short definition. What actually is a distance? So a distance measure D between two vectors x1 and x2 is a metric if the following four equations are fulfilled. So a distance between 2 points x and x2 has to be always greater or equal to 0. That's logical. A distance can't be smaller than 0. Then the distance between my point x1 and x2 is equal to 0 if and only if x1 is equal to x2. So if the two data points are the same, then the distance has to be 0. Also quite logical. The third property is the following. If the distance from my point x1 to my point x2 has to be the same as the distance from my point x2 to x1. So it doesn't matter from which direction I come. The distance has to be the same. It's also quite logical. And the fourth very important property is the triangle inequality. This has to be also true. So for example, if I have a third data point, then the distance from data point 1 to 2 has to be less or equal to the distance from my first data point to a third data point plus the distance from a third data point to the second data point. So that's the triangle inequality which we might remember from basic math, and this has to be fulfilled as well. And if all these 4 properties are fulfilled, then we speak of a metric. And this metric is very important when we compute the distances. So let's look at an example and at some distances. So which point is closest depends very much on which distance or similarity measure we use. For example, let's look at the very common distance measure. We have here again our example from before. We have here unknown data point, which is the star here. And if we now, for example, use the Euclidean distance, then we do the following. So the Euclidean distance we set here to 1, so we have unit distance. Then 3 data points lie within this distance. So we would say, okay, to this unknown data point, these 3 points are the closest. And we can compute the Euclidean distance as follows. So the Euclidean distance between my sample XA and my sample XB can be computed by taking the square root of the sum of here the differences between the feature I minus feature I from sample B. We square it and we sum it up. So the squared distance between all the points. And this is usually also written like this. We have these 2 vertical lines here. Then we write x superscript A minus x superscript B. And then we write here 2. And this indicates the L2 norm. That's also called a norm, L2 norm. So if we take now a different distance measure, like the Manhattan distance. So the Manhattan distance is nothing else than the absolute difference or the absolute distance between these 2 features here. So here we have also a Manhattan distance which is equal to 1, which is then here the squared. If we illustrate this, if we use a Manhattan distance, we see of 1 that only 1 data point here lies within the boundaries of this distance measure. So here we would not consider these 2 points, because here we only look at the absolute differences and not at the squared differences. And the Manhattan distance is less between distant features or outliers than the Euclidean distance. So the Manhattan distance is very good if we have a lot of outliers in our data set. And these 2 distances can be also generalized. That's the so-called LQ norm. So the LQ norm is also called the Minkowski distance. And this has the following formula here, where you see here we take it up, we take it to the power of Q and the full formula here to the power of 1 divided by Q. And then we have these 2 special forms. So if we set here Q to 1, then we have the Manhattan distance. So that's also called the L1 norm. And if we set Q to 2, then we have the Euclidean distance, and that's called the L2 norm. So L1 norm is the Manhattan distance. That's why we write here the 1. If we write here the 2, we refer to the Euclidean distance. And if we write here Q, we refer to the Minkowski distance. So these are now 3 commonly used measures to compute distances or similarities between features. However, there are many more distance measures. There are a lot of measures for binary data, for count data, for example, also for time series that we can do stock market predictions, for strings that we can compare text documents or DNA sequences, but also, for example, for graphs, for complex mathematical structures that we, for example, can compare chemical structures or can compute distances between chemical structures, how close they are together or how far they are apart from each other. And we will learn more of the similarity measures throughout this course. So it's very important to know what is a metric and what are the basic similarity measures. So let's go back to our nearest neighbor method. So we now know all the building blocks that we have to use, that we can predict new unknown samples. And the algorithm for this is the following. So we put now all the building blocks together. So what have we do first? First, we have to do the following. Let k be the number of all our nearest neighbors. So that's what we have defined. K is the number of our nearest neighbors, and D is the set of our training examples. For each test example, or for each query point, xq, so we could have several of those unknown points, we have to do the following. We first have to compute the distance between the test example, xq, and every training example, xi. So we compute all the distances with a distance measure that we chose. We compute all the distances. Then we select the data set, the subdata set dk. dk is now the subdata set of my data set with the k closest training examples to our test example xq based on our computed distances. And this we sort then. And then we can take the k closest training examples. So dk is now a subset. And then we predict the label y hat of our query point xq, either using the formula for the classification if we have a classification problem, or for regression if we have the regression problem. And that's all we have to do. It's a very simple and very easy method. So what are the advantages of our k-nearest neighbor classifier? The advantages are the following. The training is super fast because we don't have to really train, we just have to store the training examples. That's all the training the algorithm has to do. And also an advantage is that we keep the training data in this way. We don't throw it away, or we don't learn a different function or representation. We keep all the training data that might be sometimes useful if we like to do some other operations with it. For large K, we get quite robust classifiers for noisy data. That's also an advantage of a k-nearest neighbor classifier. And k-nearest neighbors can learn very complex functions. That are the advantages. And the disadvantages are, because we store all the training examples, we have high memory requirements. If you have now millions of training examples, we have to store them. That costs memory or disk space. And because we store all the training examples and we have to compute all the distances to all our instances in the training data set, predictions can be very slow. So the speed of our prediction highly depends also on the complexity of our chosen distance function. The more complex our distance function is, the longer our computation or our prediction takes, and it depends also on the number of neighbors k. And the prediction quality also relies on a good selection of the distance measure. If we select a crappy distance measure, then our predictions might be also not good. So it's very critical that we chose a good distance measure. And the k-nearest neighbor classifier might be fooled by irrelevant features. Let's take an example. If we have 100,000 features in our dataset, so M is 100,000, and only 1% of these features are relevant, then the problem is that distances in high-dimensional space become meaningless. That's also called the curse of dimensionality. So we have a very huge hyperspace that's very big, and then the distances between these few data points, they become meaninglessly large, and then we can't do any good predictions anymore. So what are the challenges of our classifier? Speed of prediction could be a challenge if we have a lot of data. But this could be solved by efficient data structures, which we won't learn in this course right now. There are specific hashing functions or data structures that help us to speed up the predictions. Another challenge is, how do we choose the hyperparameter k? So should be k small, should k be large? How do we select k? This we will learn in the next lecture. And it depends very much on the choice of our distance function, and this is something we also have to carefully select when we do predictions. Which distance measure makes sense for my data? There are also variants of my k-nearest neighbor classifier. For example, the epsilon ball k-nearest neighbor classifier. So the epsilon ball uses, instead of k-nearest neighbor, it uses all the data points that are within a certain distance epsilon of my test point. However, there are drawbacks. What is happening if there are no such points? So if I select epsilon to be, for example, 10, maybe there are no points that within a distance of 10. So that might be a disadvantage of this variant. There is also another variant of k-nearest neighbor that's called distance-weighted k-nearest neighbor. There we weigh the vote of each neighbor according to the distance to the test point. So if we look at the 5 closest neighbor, they are also maybe they have different distances to my test point. So why should I weigh a test point that is even far away, but belongs to my 5 data points? Why should this weigh more importantly than data points that are in the close proximity? And there are also certain other variants like feature-weighted KNN. There I can say specific features should have a stronger weight than other features. So that brings me to the end of this lecture. So what should I know? We should know about the terms and notations. What is a label? What is a sample? What's a feature? What's a dataset? How they are written down mathematically. What is a k-nearest neighbor classifier? What is a k-nearest neighbor regression? How to train the classifier, which we have learned is quite easy, and how to do predictions for new instances. We should know what is the effect of different k, what is a metric, also the effect of different distance functions, and how does the training and the prediction work for k-nearest neighbor classifier. So what's the algorithm, and what are the advantages and disadvantages and challenges of this classifier. So thanks, and see you at our hands-on tutorial where we will look at a real example how we can apply this classifier.